Basically, Dr. Haining Tian is a senior lecturer and associated professor at Uppsala University in Sweden, leading a research group of molecular devices for artificial photosynthesis. He obtained his PhD in applied chemistry at Dalian University of Technology, and then moved to the Royal Institute of Technology as postdoc and senior researcher. In 2014, he started his independent research career at Uppsala University, and he has been awarded Goran Gustafsson Prize for Young Researchers in 2016, and also the big one in 2020, Young Investigator from European Photochemistry Association in 2019, and Wallenberg Academy Fellow in 2019 as well. His research interests focus on development and investigation of sustainable soft materials, including molecules and polymers for solar energy conversion and storage. So I would like to thank Professor Haining to being a speaker, first speaker in our event. So, Professor, if you want to come up to the floor and start with your presentation, I really thank you very much for this. Thank you.
Okay, thank you, Alejandro, for the kind introduction. So, good morning, everyone. So, I'm very happy to be here to join this Photo2Fuel Final event. Today I'm talking about the design and optimizing the photosynthesizers for biohybrid systems. So, okay, so now it's a slide coming. Yes, so again, my name is Haining Tian. I'm a professor from physiochemistry at Uppsala University. And as everyone knows, so the energy is very important for our society. And so far, the fossil fuel is the main energy resource for our society. So we need to actually have the energy transition. So renewable energy is very important for us. So everyone knows solar energy is abundant, clean, but how can we actually convert solar energy, particularly how to store the solar energy? That's very important for most of countries which does not have too much sunlight, or actually for the most of countries actually don't have sunlight during the night, right? So let's check this how to convert solar energy into the different forms. So the general way actually is the solar cells. So solar cell actually which the device can convert solar energy into electricity. But you also can have the solar energy convert to the different chemicals. For example, the hydrogen and the methane, and also even the long carbon field. So we actually will focus on this artificial photosynthesis, basically on the photocatalysis based on the biohybrid system today. So why actually we want to store energy in the chemicals? If you think about your battery in your cell phone, in your laptop, if you store the electricity, so if you don't use that, actually in several days, it's gone. So the stored electricity in the battery is not long-term, and actually the battery has not enough the energy density because it's really heavy. If you convert the solar energy and store that into chemical forms, we call fuels or chemicals, that actually has very high density. So that is why the solar fuels and solar chemicals are very important to store solar energy in this case. So to do this, actually, the nature photosynthesis has done this several billion years. So that if you check the system, in the nature systems, we have the photosystem 2 and photosystem 1. So the photosystem 2 can absorb the light and oxidize water. So then you get the protons, you get electrons. Then photosystem 2 absorbs the light again. Another light actually can convert the hydrogen and the electrons to the chemical fuels. So by inspired by this nature photosystem, actually we want to do this called artificial photosynthesis. So one of the methods is the photocatalysis. So for photocatalysis, you need a photosynthesizer, so which actually can absorb the light. So how can we design photosynthesizer for this system? So the photosynthesizer needs to have the broad absorption and also excellent the stability and good charge separation. So the most important, if you want to use in the biohybrid system, so this photosynthesizer needs to be biocompatible. Of course, so the photosynthesizer needs to absorb the light, so then you get electron and hole separated. So that is very important before the catalytic reaction happens. So then you have the electrons transfer to the different catalysts. So this catalyst get electrons for the reduction reaction. The catalyst get the holes for the oxidation reaction. So the catalyst and the photosynthesizer interface were important for the charge separation and also the charge utilizations. So the catalyst, we can use metallic catalyst, we can use organic metallic complex. So we actually focus on the co-catalyst in the Photo2Fuel project. So today I'm mainly talk about the interaction between the organic photosynthesizers and the biocatalyst. So if you think about organic photosynthesizers, I think most people will come up, okay, they're also inorganic photosynthesizers. Why we do the organic photosynthesizers? Because inorganic photosynthesizers is hard to tune their absorption at the band gap. And also some inorganic materials are quite toxic. But there is actually a good example, use these inorganic photosynthesizers to do this artificial photosynthesis by the Professor Doman group. So this actually is awarded EU Artificial Photosynthesis Prize in 2022. But the problem, I just mentioned, is hard to tune the band gap. Most of the inorganic photosynthesizer absorb the light. It's not in the good visible light region, it's mostly like around 400 to 500 nanometers. But if you come to the organic photosynthesizers, particularly for the organic polymers, so which we can use the different building blocks. So these different building blocks can give our unique property of the photosynthesizer. You can tune the band gap, you can tune the energy levels. So this actually is very important for the catalytic reaction, because for different catalytic reaction, you need different driving force. So for example, I'm showing these two polymers. One is called the PFBT, one called PFODTBT. If you put two extra siphon units in polymers, you can narrow this band gap. That means you can absorb more light in the visible region. So there's a lot of other polymers. The first one is very famous in this research field that's called graphitic carbon nitride. And another is mesoporous polymers and also covalent organic framework. But most of these organic photosynthesizers in the photocatalytic reactions, you can see the figure in this corner. So you can see the particles. So that means this particle actually is quite big. So usually this particle is more than 1 micrometer. But for you, you think, okay, 1 micrometer is small enough. What's the problem? It's 1 micrometer. So that is because of the property of the organic materials. So let's check some equations. Since we need the photosynthesizer to absorb the light, you get charge separation. But for the organic photosynthesizers, different from the inorganic photosynthesizers, the dielectric constant of the organic photosynthesizer is really, really small. It means you will generate exciton, so which consists of electrons and a hole, so which has really strong binding energy. It cannot separate before it moves to the interface of the organic nanoparticles and the water or other mediate. But organic photosynthesizers have the exciton diffusion length is really short. Usually it's around 20 nanometers. That means the exciton needed to diffuse to interface. If it's longer than 20 nanometers, exciton dies. So you will not get charge separated for the catalytic reaction. So that means the 1 micrometer will give you trouble in organic photosynthesizers. So how to solve this problem? So try to make the organic photosynthesizer like polymer particles smaller, so which can give you good surface area and also good charge separation efficiency. But another way you also can do that to make the charge separation not at the interface of nanoparticles as immediate. You should do that actually within the nanoparticles. This we call strategy is heterojunction, but you're still facing a problem to transport the electrons and the holes to the interface. Okay, so the first proof of concept from my group, and we use this nano precipitation method to prepare these PFBT polymer particles we call PDOTs. And we can get the polymer particles really small, as around 40 nanometers. So if you see the pictures under the left corner, so we also can use the different polymers to get different polymer particles, which can absorb different light. So you can see that solution is really transparent because the particle is really small. And once we use this for the catalytic hydrogen production, actually we increase the catalytic performance by 5 to 6 orders of magnitude. So this is a very important step for my research, actually jump to the photocatalytic reaction by organic photosynthesizers. So then our group spent like almost 10 years to do the different structure design and composition optimization and also mechanistic study to how the organic photosynthesizer interact with different catalysts, how the physical properties inside of the organic nanoparticles for the different reactions. But recently we actually focused on this biohybrid system because, as I mentioned, these organic photosynthesizers can be designed to be biocompatible to work with biocatalysts. So now I will show several examples how the organic photosynthesizers drive the organic, biocatalyst for different reactions. So before we put the polymer particles in the biohybrid systems, first we started called the carbon dots. So the carbon dots is not polymer, it actually is synthesized by the hydrothermal method. So you start from the small acid, then you put that in the autoclave, you heat it, and you get it really small, but it's very conjugated nanoparticles. These particles are really small, it's 2 or 3 nanometers. But the problem is it does not absorb much light. But it can interact with the biocatalyst well. So these carbon dots can interact with, like, for example, here we use the enzyme. So it can transfer electron directly to the enzyme to produce hydrogen. We spend time to understand the interface transfer between the carbon dots and the enzyme. As I mentioned, so the carbon dots, it cannot absorb much light. So if you want to further improve the efficiency for the biohybrid system, you need a photosynthesizer that can absorb more light in the visible region. So that's why we start with the P dots. So the P dots, as mentioned, we can prepare that from nanoprecipitation method. Then we can also tune the surface charge. It can interact with the biocatalyst well. So here is an example. We use this called heterojunction polymer particles. We call it P1 and P2. From the current EM, you can see from EM, so here is the pure polymer particles. Here is the polymer particles with the enzyme. You can see the enzyme actually attached on the surface of the particles. But these polymer particles can absorb the light up to the 500 nanometers, even to 600 nanometers if we tune the structure. From the photophysical study, we know inside of the organic nanoparticles there's energy transfer, and the charge transfer happens. It forms the charge separation between the polymer 1 and the polymer 2. That is very important for the next step to transfer electrons to redox mediates. So here the redox mediates we use called methodology. So to understand the electron transfer rate, so we use the laser photolysis to get this reaction rate constant. Then we also calculate the reaction rate. So we also add the hydrogenase inside. We also can calculate the electron transfer rate constant or the electron transfer rate from the reduced methodology to the hydrogenase. So if you check these two values, they are similar, so it seems they actually match well. But if you check that system, we also have a sacrificial donor we call a triethylamine. So these actually have very small driving force to reduce the polymer particles back to the ground state. So we think that this could be the main rate limiting step. So when we increase the concentration of the triethylamine, you can see the hydrogen generation is significantly increased. So it gives the information actually we can tune the interface, also can tune the different components in the biohybrid system to improve the catalytic reaction. So once we have these polymer particles for the enzyme, so we are thinking, can we use this for the bacteria? So bacteria is very important. It can do a lot of interesting reactions that can fix the CO2 into the different products with the carbon, from the carbon 1 to the carbon 6, even the polymers. So the bacteria we use here is called Ralstonia atropha. We collaborate with the Professor Tian and the Professor Shu Wang from the CCUS. So we designed the organic polymer particles, also still tune the surface charge. You can see from the image, so the organic polymer particles stick on the surface of the bacteria because they have the opposite surface charge. So with the help from organic polymer particles, we can get increased production of the polyhydrobutyrate. So that actually is called the biopolymers. It's a very important product. Based on the research from the polymer particles and also the biohybrid system, so we actually run this Photo2Fuel project so together with a lot of the partners in this consortium. I will show one example how we design the photosynthesizers and to test the photosynthesizers in the biohybrid system in this project. So in this project, we focus on the two bacteria. One is for the acetic acid production, one for methane production, but I will leave that for my colleague to present later on. So we first to design the polymer particles from these organic molecules called the PHOTOsynthesis. So that is phenoxyethanol-based polymer, molecule. So that we still use nanoprecipitation method together with the polymer amphiphilic polymer surfactant that can get this called nanorod. So you can see from the current EM. So that is the nanorod shape. So this actually can interact with the biohybrid system. So first we try to use this carbon monoxide dehydrogenase. Because that actually is a very important enzyme in the bacteria to convert CO2 to CO. So still we use methodology to transfer the electrons between the photosynthesizer and enzyme. So first we check if that's possible for the PHOTOsynthesis to give the electron to methodologies. Then we use the methodology to quench the excited state of the polymer particles. So you can see we also can tune the different surface charge of the PHOTOsynthesis. So the positive charge, the PHOTOsynthesis give very good quenching efficiencies. That means it can transfer electron to methodology more efficient as compared to the negative charge, the PHOTOsynthesis. Once we put that together with the carbon monoxide dehydrogenase, we can see we get the hydrogen out. But that's quite interesting for the negative charge PHOTOsynthesis. It does not have the CO produced. Another thing we can check here, so the methodology and the carbon monoxide dehydrogenase. So the driving force from methodology to the COCODH, so the dehydrogenase is very small. So if you want to improve the CO production, we think maybe the driving force is a problem. So we used another redox mediator called the dicot, so which has the little bit more negative reduction potential than that of the methodology. So if you check the CO production now, so we increased this CO production significantly. So that also gives another example, the interface between the organic photosynthesizer and the biocatalyst is very important. So with this, I will conclude my talk. So organic nanoparticles were important. You can make that as compatible to drive the biocatalyst. So the carbon dots I just showed is very small. I can interact the biocatalyst well, can give the electron directly to the enzyme. But the problems, the weak absorption in the visible light cannot give much more catalytic reaction as compared to other systems. And organic nanoparticles prepared from nanoprecipitation method are tunable. So we can get a different absorption in the visible light, which is very important for future to improve the biohybrid system performance. And of course, we know that there is big room for this biohybrid system to be improved, so both from the design of the organic photosynthesizers and also improve the interface between the organic photosynthesizers and the biocatalyst. So with this, I would like to thank my group. Particularly, I give this thank to my colleague, Maria Pawluk, and she actually is the main person working on the biohybrid system. And of course, my co-collaborators, and of course, the Photo2Fuel project. That is a very interesting and challenging journey for my group, I think also for everyone. I also give the thanks to my partners in this work package, also Professor Haining Tian from the RCCS, and also Dr. Maria from the TZE. So it's very, very interesting and it's a very honored to work with you all here. Okay, with this, I would like to close my talk. So I would like to think that is the question will be coming later on. Yes.
Thank you very much, Professor.
Thank you.